The rudder is located on the aft portion of the vertical stabilizer and moves in response to pilot pedal inputs or yaw damper commands. The rudder is connected to the Rudder Power Control Unit, or PCU, which in turn is attached to airplane structure. It is the PCU that translates pilot or yaw damper commands into rudder motion. Following is an overview of normal PCU response to a pilot input. The rudder PCU is shown with the cylinder housing removed. A pilot input at the rudder pedals in the flight deck results in a command through cables and linkages to the external summing lever, shown at the extreme right, which moves the input link, the blue arm connected to the external summing lever, and in turn the input crank, the gray arm connected to the input link, and internal summing links, which moves the primary and secondary slides in the control valve, the green canister, providing hydraulic pressure to the rudder actuator. When the control valve ports hydraulic fluid to the rudder actuator piston, system pressure moves the rudder to the commanded position. The external summing links move with the piston. This movement provides feedback to the input control rod to move the primary and secondary slides to the null position. In this depiction, a pilot command resulting in the rudder piston retracting moves the rudder to a trailing edge right position. In this more detailed view, the command to the input crank is shown. The input crank moves the internal summing links, which move the primary and secondary slides in the control valve. For a normal or slow rate input demand, only the primary or inner slide moves. For a higher rate of demand, both the primary and secondary or outer slides move. The internal summing links move the primary and secondary slides in the control valve to the commanded position, allowing hydraulic pressure to move the actuator piston. When the rudder achieves the commanded position, determined by feedback through the summing lever, hydraulic pressure is shut off and the rudder remains at the commanded position. When the pilot returns the rudder pedals to neutral, the feel and centering units supply force to the external summing links, moving the primary and secondary slides to a new position to center the rudder. Viewed from above, it can be seen how a pilot command is fed through the external summing lever and feedback mechanism to move the primary and secondary slides in the control valve. From above, it is clear how the input crank is moved, and in turn moves the internal summing levers to move the primary and secondary slides in the control valve inside the green canister. It can then be seen how the control valve is commanded back to the neutral position via inputs transmitted through the input crank, external summing lever, and rudder actuator piston. In this view, it is also clear how the rudder actuator piston moves to the commanded position and closes the control valves. Notice the motion of the internal summing links to hold the rudder in position. When commanded back to neutral, the internal summing links move to reposition the primary and secondary slides, which move the actuator piston to the new position. In this detailed view of the internal summing links, the input crank is shown moving the control valve to create hydraulic flow, shutting off the control valve when the commanded deflection is achieved, and reversing the process when the rudder is commanded back to neutral. Note how the summing links cause the motion of the primary and secondary slides. The next series of views depicts how the yaw damper can move the rudder independent of pilot input. The yaw damper actuator, the horizontal rod with the disappearing outer case, when receiving a command to correct an airplane yawing moment, moves to transmit a motion through the walking beam, the vertical rod with an external spring, and into the internal summing links. The summing links move the primary and secondary slides in the control valves independent from a pilot command. The rudder travel resulting from a yaw damper command is mechanically limited by stops on the yaw damper actuator. In this more detailed view, it can be clearly seen how the walking beam transmits its inputs through the internal summing links to the control valve. This expanded view of the overall PCU shows the type of motion made by the walking beam and how it transmits its motion into the summing links. Further, it shows how the inputs to the control valve are transmitted to the rest of the actuation mechanism to cause rudder motion during normal operation. Finally, This detailed view of the walking beam's link to the internal summing levers shows how the walking beam input is transmitted into the control valve through the summing levers. The primary valve usually functions on its own without any associated motion of the secondary valve. For high-rate demand situations, the secondary valve also moves, allowing an increase in hydraulic pressure to the rudder actuator. This example illustrates both a normal rudder response to a command and the rudder reversal postulated by the NTSB. In the scenario for normal rudder motion, a pilot command to move the rudder to the left, rudder trailing edge left, results in an extension of the primary slide, opening hydraulic ports and allowing hydraulic fluid to flow under pressure into the rudder actuator, where the rudder actuator rod extends and moves the rudder in the proper direction. In the reversal scenario postulated by the NTSB, the pilot makes a high-rate rudder command to the left. The primary valve extends to its travel limit and should be followed by a movement of the secondary valve. However, the secondary slide jams to the outer case, allowing the primary valve to over-travel, resulting in a misalignment of the hydraulic ports. This allows hydraulic flow in the wrong direction and causes the rudder actuator rod to retract rather than extend and moves the rudder in a direction opposite to that which has been commanded.